Okay, all right, let's start. Let's recall what we did last time. Last time we did introduction to the cryptography, some baby example of cryptography. Okay, first we introduce the Morse code. Okay, the Morse code. Then we talk about the Hill cipher. The Hill cipher. Okay, the cipher. Okay, the Hill cipher is and then we talk about the direct substitution. Direct substitution. Now it turns out the direct substitution, although at first sight it can be hard to, break this system. However, it turns out if you do analysis, okay, the frequency analysis, it turns out this is very easy to break. Okay, very easy to break. So then we introduce the Hill cipher. The Hill cipher is we use a matrix. Use a certain matrix integer, and then if you have a message, so we encode this message, a string of text, okay, a string by a bunch of numbers, okay, a bunch of numbers, so that we have a vector, okay, so we get a vector. Then, so if Alice want to communicate with Bob, then Alice and Bob, they share a matrix and its inverse. Okay, now Alice encode a message by multiplying the message vector by the matrix M, and then Bob decode this message by applying the inverse matrix. Okay, now we by our choice, the inverse matrix is also integer. Okay, integer, so that Bob can recover the message Alice want to send to him. Okay. It turns out this the Hill cipher is not good enough. The reason is that the private key is shared by Alice and Bob. Okay, in many situations that this is unreliable. Okay, if this is unreliable, so you want make sure the private key is shared as shared only by yourself. Is only by yourself, not anyone else. Okay. So this is not a very secure algorithm, and also there's a trouble if you want to communicate with different people, then you need to change the private key. You need to change a different key. You don't want to use your private key with a lot of people, so that actually if you use your private key to many people, it means your private key is almost public. Okay, so it's not secure. Then we have the public key algorithm. Okay, public key algorithm. Such that everyone has their own private key. Okay, the private key is only by one people, not shared by Alice and Bob. So this makes this more secure. Now this is what we introduced today, the RSA algorithm. Okay, so you see the three names. So this algorithm published in 1977. Okay, the mathematical structure of RSA is really simple. Okay, now we've actually introduced today the RSA algorithm. Okay, the key thing that RSA algorithm is actually modular arithmetic. Modular arithmetic. We defined the modular arithmetic last time. So if A congruent to B modulo N, this is equivalent by definition that the number N divide the difference. Okay, i.e. AB is a multiple of N. Okay, A minus B is a multiple of N. And we give several examples of this congruence relation. Okay, if we mod a prime P, if we mod an integer by a prime P, then we have a complete residue system modulo P from 0 to P minus 1. Now this is complete residue system. And we find that if two numbers, they are not a multiple of P, and if we multiply any number that is not a multiple of p, then they are still not a multiple of is not a multiple of p. Okay, i.e., if we have two numbers mn, they are distinct modulo p, i.e., their difference is not a multiple of a p. Then if we multiply any a which is not a multiple of p, this product is again not a multiple of p. So p doesn't divide a times m minus n, i.e., so we have this a times m is not congruent to a times n. Okay, so this tells us that multiplication by a non-zero residue, okay, multiplication by a permutes the residue system. Okay, and then we give some example. Okay, when for instance p is 5, so we multiply by 2, you see we permute, so 0 always goes to 0. Okay, because a multiple of 5, you multiply another number, you still get a multiple of 5. So 0 goes to 0. Then all other non-zero residues just permuted around. You see, we have permutation by you see, this multiplication by 2 is a permutation of these non-zero residues. Okay. You see, if we have non-zero residue modulo p. Now, if we multiply the residue by a, so this permute this non-zero residues. So somehow there is one. There's a one number that we multiply by a, so that we get actually 1. Okay, we get a 1. A times b congruent to 1. This would be unique. Okay, this would be a unique a or a unique b. Because if you have another b, then we actually have so this uniqueness. So uniqueness we can find by. So suppose if you have another b prime, suppose another b prime. So a times b congruent to 1 mod p. So and then we have a b prime minus a b. This will be congruent to y minus 1. This is congruent to 0 mod p. Okay, this means a times b prime times b congruent to 0 mod p. Now this means p divide the thing. Okay, p divide the thing. Okay, this thing a times b prime minus b is a multiple of a p. Okay. Now, if a prime divides a product, then a prime necessarily divides one of this factor. Okay, so this tells us that p divide a or p divide b prime minus b. Okay, now we don't remember p is not divisible by a. A is not divisible by p, because we assume that a is not 0. A is not congruent to 0 mod p, i.e. P does not divide a. So this tells us that p divides b prime minus b. Okay, so this actually tells us that b and b prime, they differ by a multiple of p. So this tells us b prime is congruent to b. Or if you write it like this, b prime minus b congruent to 0 mod p. So you actually have b prime congruent to b. So this actually shows the uniqueness of the inverse. Okay, this shows the uniqueness of the inverse. Okay. Okay. Let's do this example. The order of an element. Okay, so you see the non-zero element has an inverse. Okay, the non-zero element has an inverse. Now let's actually introduce the definition of a group. Okay, let's now introduce the definition of a group. So a group. What is a group? What is a group? Now here, this group is actually a mathematical object, important mathematical object. Okay, a group. We actually have many examples of groups. You see, for instance, this example, real number as a group. So for instance, with respect to addition, so any number has an inverse. Okay, for instance, 5 has inverse 5, negative 5. So because z plus, z get a 0. Okay, so here 0 is the identity. So you think this as translation. You translation, so 5 means translation to the right by 5 units. Negative 5, you think translate left by negative 5, but by translate to the left by 5 units. Okay, so you translate it to the right and then translate it to the left, which means no translation by 0. So the identity element is element is 0. Okay, here if you add identity element, so there's no change. Okay, so this is identity element. Okay, so every element has an inverse. So every element 5 has an inverse. So every element has an inverse. Has an inverse. Unique inverse. Inverse. Now, of course, we have associative property for addition and subtraction. For, it's associative this with respect to this addition. So the real number as, with respect to addition form a group. So this is a group. Okay, this form a group. So you can think this R as a group with respect to addition. So this is actually the translation on y direction on a line. Okay, translation of the number line. Okay, this is translation. This talks about certain symmetry. Okay, a group. Okay, so this translation. Now, of course, R2 we can also, R2 with respect to addition. This is also a group. Okay, a group with respect to translation. So you can translation by a vector. Okay, you can translate by a vector. Now the 0 element is 0 vector. Okay, translation. 0 vector as identity element. So any element you can translate. For instance, a point. You translate as so this is 0. You translate it to 1 1. This point 1 1 1 1. You can also translate it back. Okay, you can translate it back by the negative translation. Okay, negative translation. So we also have associative relation with respect to this addition. Okay, associative. So this is also a group. Okay, from inverse. Okay. Any other example of a group? We also have, for instance, this matrix. For instance, let's see this SL to Z. So this is the 2 by 2 matrix with integer coefficients. With the respect 2 by 2 matrix with integer entries. So this is also a group. Now this is, the multiplication is matrix multiplication. So the group operation is the matrix multiplication. Now SL2Z means the determinant is 1. Okay, so this with determinant 1. Determinant 1. Now if you do the inverse, okay, it is again integral matrix. Okay, integral matrix, and also it is determinant is 1. Okay, determinant is 1. So its inverse, it still lies in this in this set. Okay. Now product matrix multiplication. You know, two matrix. You know, they multiply. They again lies in this this set. Okay. So this is a group. Okay. This is a group. Now, what symmetry does this group tells us? Okay. What symmetry does this group tells us? Okay. This is group of symmetry of a lattice on the two-dimensional plane. Okay, lattice. So this is actually tells you lattice matrix of symmetry of lattice on the on plane. So it's on plane. Two-dimensional. All we see is a two-dimensional lattice. Two-dimensional lattice. So now a lattice you can. So it's a Z2 structure. So it's integer plus integer. So all you think it as it tells you the symmetry of this thing. So it acts on these 2x2 vectors, two-dimensional vectors with integer coefficients. This is Z, this is Z. Okay. So integer. So this, for instance, 1, 2. So you have a 2x2 matrix. You act on this vector space. Okay. You get another vector. So this tells you this kind of thing. Vectors in integer coefficient. It's actually two-dimensional lattice. Two-dimensional lattice. Okay, we have a lot of examples of groups. For instance, if you study what's that called? There are many examples of groups. For instance, if you study chemistry or physics, you have certain systems, like molecules. They are sometimes certain molecules. They have symmetry. Their symmetry, we can talk about their symmetry by groups. Okay, groups. By groups. Okay, for instance, permutations. So that's symmetric group in letters. This is a group. Okay, symmetric group. Symmetric group in letters. In letters. Okay. So this is a group. Now, group theory is important part in algebra because it talks about symmetry. It's the most natural language to talk about symmetry of objects. Okay, for instance, let's talk about this example. The non-zero residues modulo a prime form a group. This example, the non-zero residues mod a prime P form a group with respect to a multiplication. Okay, example. P equals 5. So this is so we have this group. 1 bar, 2 bar, 3 bar, 4 bar. Okay. So this bar means mod 5. So we already know, for instance, this is multiplication. So 3 times, for instance, 3 times 3 squared, we get a 9. Okay, 9 mod 5. This gives us 4. Okay, subtract a multiple of 5, so we get a 4. So 3 times 3, we get a 4. 3 cubed. This is 3 squared times 3. So this is 4 times 3. 4 times 3 is 12. 12 is subtract multiple of 5 is actually 2 mod 5. Okay, then you see 3 to the power 4. Then we get this is 3 to the power 3 times 3. This is 2 bar. 3 to the power 3 is 2. So this is 2 bar times 3 bar. So this is actually 6 bar. 2 times 3, you get 6. Okay. 6 is congruent to 1 mod 5. Okay. So the unit here, the unit, the identity element is 1 bar. So you multiply anything by 1 bar, it doesn't change. Okay. So 3 bar times 1 bar. So we get a 3 bar. Okay. No change. So this identity element does not change anything, multiply the thing. Okay. So this is the identity element. Okay. Okay. So you have 2 bar times 3 bar is the identity element 1. So this tells us that 2 bar is the inverse of 3 bar. Okay, is the inverse of 3 bar. Okay. Okay. Now we talk about this. Okay, if we have a composite number, what happens? So this example, what happens if we have a composite number, mod 10, for instance? Example, n is 10. Now in this case, now for instance, 2, this is not 0 mod 10. So this is non-zero element. Okay. So 5 is non-zero. 5 is non-zero. Okay. 5 is not equal to 0 mod 10. However, 2 times 5, this will be 10 bar. This will be 0 mod 10. Mod 10. So this means 2 and 5, they are not invertible. They are not invertible. Okay, not invertible. So remember, to form a group, we need invertible elements. Okay, invertible element. So that you see 2 and 5, they are divisors of 10. Okay, they are divisors of 10. So we will try to avoid divisors. Okay, divisors. We find the residues modulo 10 that is coprime with 10. Okay, so the fact is then the residue classes coprime with 10. Then the residue classes coprime, which is not a factor of 10, coprime with n from a group. So in this case, now coprimes, numbers that less than 10, coprime is 10. So we have this is, for instance, 1. 2 is not okay. 2 is a factor of 10. 3 is 3 okay. 3 is coprime. Okay. 4 is not okay because 4 and 10 they both divide by 2. 5 is not okay. 6 is not okay. 7 is okay. 8 is not okay. 9 is okay. So we have 4 numbers. Okay. 1, 3, 7, 9. Okay. Modulo 10. They form a group. Okay. So you see 3 bar squared, we get 9 bar. Okay. 3 bar cube, then we get a 9 bar time. You see this is 3 bar squared times 3 bar. So this is 9 times 3. 9 times 3 is 27. 27 mod 10, we get a 7. Okay. So 3 to the power 4. Then you get a 3 to the power 3 times 3. It's 7 bar times 3 bar. So it's the 21 bar. 21 is congruent to 1 mod 10. Okay, mod 10. So you see, then we give some definition. Okay, the order of the group, the order of an element, and the order of a group, the order of an element. The order of an element, you see, the smallest number such that, for instance, 1 power of 3, we get the identity element. Okay, so if we have an element G in a group G, so this is the order N, order G, order of G is the smallest, is minimum of the minimum number of N in, let's see, positive integers such as G to the power 1, G to the power N is the identity element. Okay, of G. Okay, we already see certain permutations already. Okay, permutation matrix. Okay, now permutation matrix, their order, you know, is the smallest number such that we do this number of permutation such that we get the identity element, i.e. no chain. Okay, no chain. So this is the order of an element. Now, what is the order of the group? The order of a group is how many elements that are in this group. The number of elements in a group. The number of elements. The number of elements in a group G. So G is a set. Okay, G is a set. Okay, a group is a set that with certain group operation that satisfy certain conditions. Okay, is a set, is in a group. Number of elements in the group G as a set. Okay, as a set. The set. Okay, so the example you see the this group, the residue classes modulo 5. Okay, so it has 4 elements. 1, 2, 3, 4. Now 0 residues. So the order of the group order is, you know, the set has 4 elements, so the group order is 4. Okay, now let's check what is the order of elements. So you see, let's see now this example, p equal 5. What's the order of a 4? What is the order of a 4? Order of 4, you do the power. Order of 1, order power 1. So 4 is 4, not identity. Now 4 squared, you see 4 squared is 4 times 4, so we get a 16. So 16 bar. 16 bar, subtract a multiple of 5, you see, multiple of 5, 15. So subtract 15, so it's 1 mod 5. Okay, so you see order of, so 4 bar has order 2. Group element has order 2. Order 2, okay. And you see order 3, so the element of 3, you see, we need to do the power 4, then we finally get 1, okay, identity element. So we get 3 bar has order 3. Has order 4. Has order 4, okay. Now let's see this example. 1379 mod 10. Okay, what's the order of the group? The group has 4 elements, so the group has order 4. Okay, now what's the order of the element 3? You see, we see 3 to the power 4 is the identity element. So you see 3 has order 4. Now what's the order of 9? 9, you see, 9 squared is 81. 81 mod 10, so this is actually 1. So actually 9 bar has order 2. 9 bar has order 2. Order 2. So the group order is 4. Group order is 4. Okay, group order is 4. Okay. Okay, so next we will talk about the Lagrange theorem. One of the Lagrange theorem, which says this. Lagrange theorem. Lagrange theorem. Okay. For a finite group, a finite, finite as a set. Okay, for a finite group, the order of a group element, order of a group element, is a factor. Of the group order. Okay. The example that we did is, you see, so you see the example, the first example. So the group order is 4, has 4 elements. So you see, element 3 has order 4. Okay, 4 divisible by 4. Okay, 4 is a factor of 4. So the element has order 4, which is a factor of group order. Now you see the element 9. The element 9 has order. Sorry, the element of 4 has order 2. Okay, has order 2. Order 2. 2 is a factor of group order 4. Okay. So you see the example, the group modulo 10. Okay, modulo 10. The coprime residues modulo 10. So you see 9 has order 2. Okay, the element 9 bar has order 2. Okay, 9 squared is 81, which is the identity element. Okay, so 9 has order 2. Order 2. 2 is a factor of the group order. The group order is 4. Okay, so this is what the Lagrange theorem says. Okay, for group order. In a moment, I will explain why we actually have Lagrange theorem. Right now, we just assume it. Okay, assume this Lagrange theorem to understand what a RSA is. Okay, now let's talk about this function, Euler function, Euler phi function, Euler phi function. Okay, you see, Euler phi function is a function defined on positive integers. Okay, phi n. So for n in, let's see, in z positive integers, so the Euler phi function, the Euler phi function is defined as the number of, so we have phi n is the number of element that is coprime with n. Okay, so you have the number of m from 1 to n such that okay, so this is the number of m. Let's do it here. So we count how many number m such that the m is from 1 to n such that they have no common divisor. Okay, GCD, great common divisor of the thing is 1. They have no common divisor. Okay. So this is, we count how many numbers that is coprime with a number n. Okay, coprime with number n. Of course, we should assume that n as a number should be between 1 to n. Okay, for instance, For instance, what is phi 5? What is phi 5? How many numbers co-prime with 5 from 1 to 5? Okay, phi 5, because every number from 1 to 4 is actually co-prime with 5. Okay, 5 is not co-prime with 5. So 1, 2, 3, 4, they are both okay. So we have 4 numbers. So phi 5 is 4, okay? 4, which is 5 minus 1. 5 minus 1. Here 5 is a prime. 5 is prime. So how many for a prime? What is phi of p for prime? For prime, then the number of the numbers that co-prime with p is actually, as long as it's less than p, 1 to p minus 1. Then these numbers, they are co-prime with p. Okay. So phi p will be Euler phi function of p. It will be p minus 1 if p is prime. P is prime. P is prime. Okay. Okay. Now from Lagrange theorem, from Lagrange theorem, so if A not congruent to 0 mod P, then you know the group A is an element. A is an element. A is an element of the multiplicative group. Multiplicative group. You know, 1 bar, 2 bar, p minus 1 bar. Okay, so this form a group by multiplication. So A is an element in the multiplication group. So the group order is p minus 1. So the element A is in this group. So the order of A is a factor of p minus 1. Okay, is a factor of p minus 1. So you see, this actually tells us that A to some order n congruent to 1 for some mod P. For some n divides P minus 1. Okay, so suppose P minus 1 is K times n. Here K is in, you know, Z positive integer. So you see A to the power P minus 1. This will be A to the power, so this will be A to the power n times K. Okay, this will be A to the power n to the power K. Modulo prime P. This will be now A to the power n is a multiple of P. Okay, so you modulo P, you get it, mod P. Modulo power of P. Okay, modulo power of P. Okay, or if you write it as A to the power n is you know, 1 plus 30 number L times multiple of P. Okay, to the power K. Then you use binomial expansion. You see this is 1 plus 30 multiple of P. So this is equal to 1 mod P. Okay, so you actually get this thing. Okay, AP congruent to 1 mod P. If for A not divisible by for A which is not a multiple of P, for A not congruent to 0 mod P. Okay, so this is actually called Fermat-Little theorem. This is called Fermat-Little theorem. This is called Fermat-Little theorem. This theorem. Fermat has a lot of theorems. Fermat-Last theorem, you see, is actually a theorem that puzzled people for 3.5 centuries. finally solved by Angelo Wiles. Okay. Okay, so this is Fermat-Little theorem. Fermat-Little theorem. And actually, Fermat-Little theorem is actually really useful. We often use Fermat-Little theorem to determine if a number is prime or not. Okay, prime numbers. So choose a number A, choose a number A coprime with number P. Okay, then do this modulo arithmetic and see, check A to the power P minus 1 and see if it's congruent to Y or not, mod P. Okay, remark. Okay, we often you use Fermat-Little theorem as a necessary condition, to check if a number is to test if a number is prime or not, is a prime or not. Okay. Now, if you choose a non-zero number modulo the prime, modulo this number, and compute it. Okay, suppose you have a number n, then compute it. A is not a zero, mod n. Then you check a to the power n minus 1. Check a congruent to 1 mod n or not. Check whether it is true or not. It's true. It's true or not. If it's true, then it's possibly prime. Okay. If it's not true, then it's not prime. N is not prime. Okay. Okay. Now sometimes if n it's possible that a number n satisfies Fermat-Little theorem. However, this number is not prime. Okay. So this Fermat-Little theorem gives us a necessary condition of a prime of a number being prime. So we often use this thing as a first test to test if a number is prime or not. Then we use other tests to double check. Okay. Okay. And see, so this Fermat-Little theorem. Now the next condition, the next thing is, let's explain the idea of RSA. Okay, yeah. If we have a composite number, how do we find? So if we have a composite number, then the residues coprime to n form a group. Okay, so if for general n, if we have n, okay, so remember the coprime residues, the residue classes coprime with n form a group. Now the order of this group, the order of a group is counted by phi n. Okay, is of order phi n. Okay, order phi n. Okay. Now remember, the coprime residues is actually exactly counted by the Euler phi function from 1 to n. Okay, from 1 to n, and coprime with n. GCD means great common divisor. Okay. So their GCD, great common divisor, is actually 1, means they do not have common divisor except 1. So this means they are coprime. Okay. So the number of coprime residue classes is actually counted by the Euler phi function. Euler phi function. Okay, so then we use Lagrange theorem. By Lagrange theorem. By Lagrange theorem. Lagrange theorem. The element has order, you know, a to the power phi n is congruent to 1 mod n. Okay. If a and n coprime, if GCD is 1, if GCD an is 1. Okay. So we get Lagrange theorem. So we will use this in a moment. Okay. Fermat-Little theorem is a special case of this thing. Okay. When you take n prime. Okay. If n is prime, if n is p, n equal to p, a prime, then we get the Fermat-Little theorem. We get a Fermat-Little theorem. Phi n in this case, phi n is p minus 1, a to the power p minus 1, congruent to 1, mod p. Okay, here a is non-zero, a is non-zero mod p, a is coprime with p. Okay, so so you check. Okay. Now we are okay to talk about RSA now, except one thing. Okay, so we computed this special case. So one more thing. Let PQ be PQ, P and Q be two distinct primes. Let N excuse me, be the product of P and Q, and compute the Euler phi function, phi of N. Let N be the product, P times Q, be the product. Find phi N, Euler phi function at N. Okay, remember, okay, so phi N counts the number of elements in from 1 to the number n. Okay, number n is PQ. N is equal to PQ, such that M and PQ coprime. GCD great common divisor is 1. Okay. Okay, so we count how many numbers lies in between 1 to PQ, such that coprime is PQ. Now we actually can do this easily. So the total number is PQ. Okay, from 1 to PQ. So we have this total numbers. Okay, total numbers. In total integers. Total integers in 1 to PQ. This is interval. Now, first of all, how many? So we check how many M that is not coprime with PQ. Okay. Now either we have this condition. So how many numbers that is a multiple of P? Okay. Multiples of P. How many multiples P? Multiples of P. Multiple P. How many multiples of P are there in this interval? Well, we count how many multiple of P. Okay, so we need a number P, K times P is from 1 to PQ. Okay, PQ. So K, you see, P is greater or equal than 1 over P to PQ over P, which is Q. So you see K is from 1 to Q. Okay, so they are exactly Q numbers. Q numbers. Okay. how many multiples of Q? Multiple of Q. Okay, multiple of Q. So let's see, LQ is from 1 to PQ. Now you see L is from P divided by Q, from 1 over Q. Okay, so this actually, you see L is from 1 over Q. 1 over Q is greater than 0. So it's 1 to P. So we have exactly P numbers. Okay, P numbers. P numbers. P numbers, which is multiples of Q. Okay, now actually we have one. If you subtract PQ by P and Q, actually we are subtract too much, because the Q numbers, the multiple P and multiple Q, they actually overlap. These two sets overlap. We have a number which is both multiple P and multiple Q. Okay, so the number PQ. So the number PQ is both multiple P, and both multiple P and Q. So we need the total number PQ minus P minus Q. Then we are actually subtract too many. Then we add a multiple. So the multiple PQ, the number PQ is actually subtracted twice, okay, from the original set. So we need to add it back. So add 1, okay. So this should be the total number that is coprime, okay, coprime with. We just deleted all possible multiple things that has common divisors, okay, non-trivial divisors. Then the remaining thing should be the numbers that are coprime with PQ. So the number phi n is this thing, okay. So if you factor this is actually P minus 1, Q minus 1. Okay, so this is actually phi P minus phi Q. Fact. The phi function, phi is multiplicative. I.e., if you have two numbers, i.e., if Mn GCD Mn is 1, okay, then the product phi m times n equals phi m times phi n. Now we will not prove this. If you start in number theory, you will actually have a chance to find this proof. Okay, we already use a baby case of this fact. Okay, so when we choose Mn to be phi q, okay, so PQ choose M equals P, N equal to Q. Then we get a phi PQ. This will be, they are coprime distinct. Okay, this will be phi P times phi Q. Okay, so this will be P minus 1, Q minus 1. Okay, now we already have enough background for the RSA algorithm. Now we actually explain what RSA algorithm is. Okay, and then we will then give one example of how we apply RSA. Okay, so the idea of RSA is the following. Okay, if we have two primes, okay, it's very easy to multiply them. Okay, so RSA, baby example of RSA. Idea of RSA. So the baby idea of RSA is the following. Yeah. Okay. Now we start RSA. Let's PQ be two large primes. Okay. Now, fact. If we if we have two primes, let n be p minus q. Multiplication of these big primes, this is very easy. Okay, you can use computer. That's very easy. Okay, easy to compute. Easy to compute. Easy compute. Now, conversely, now if someone tell you n give you now giving n giving a number n if we don't know, if we know it's product of two primes, if we want to factor it, now it's difficult to factor n. Okay, so even if you know that n is p times q, okay, which we know is known to be a product of two primes, last prime. Now it's very difficult to factor n. Okay, factor n to be find some p and q. Okay, so this is difficult. Because here we need to try a lot of cases. You know, see if n is divisible by 2, 3, 5, 7, 11, 13. Okay, all these primes, and test whether if n is divisible by these primes. Okay, we need to try a lot of cases, so it's computationally expensive. Okay, if n is large. For small n, you can use calculator, use a computer package. But for large n, so this is difficult. Okay. Now one way is easy, the other way is difficult. Actually, you can do something. Now this is, now suppose we have the following process is how we do the RSA. So suppose we have Alice and Bob. Okay, Alice and Bob. Suppose they want to communicate. Now, Alice, what Alice does is Alice chooses two primes. Alice chooses two primes, large primes, and this is private. It's only known PQ. This is private. Okay, private to Alice. Bob doesn't know this. Keep private to everyone. So private to Alice. Okay, is private. So this Alice keep it as private key. Okay. Now, n compute. So Alice can compute. Alice compute n to be p times q, and publish n. So this n is public. Okay. So he can give this n to anyone. Okay. So even if Alice published this n on New York Times, for instance, now no one actually can factor it p times q. Okay, because it takes us too long time to factor, even with supercomputer. Public. So n is so large. And it takes forever to factor it. Okay, it takes forever. It's so large, and it takes forever. Takes longer time. It's possible that the time is longer than the life of the universe. Longer time to factor with the current computation power. Okay. So now n is public. Okay. Now what is phi n? Phi n we already know. Phi n is phi p times q. This is a p minus 1, q minus 1. Now this is the private. Private to Alice. This is the only known to Alice. Bob doesn't know. Now even if you have n, we can actually not compute phi n. Okay, we cannot compute phi n. Why? Because first of all, you cannot count. Okay, its n is so large. For small n, we can count how many numbers are co-prime with n. Now, if n is large, so to count is time consuming. Okay, we cannot directly count by brute force. So even if you know n, phi n cannot easily computed by other people. Okay, even if you know n. However, Alice can easily compute this because Alice know p and know q. Okay, so Alice can easily compute. Alice can easily compute this because Alice know his private key p and q. Can easily compute this. This number using p and q. Now this p and q is private, is not known to other people. Okay, so Alice can easily compute. Other people cannot easily compute. Okay, now if you direct compute phi n by the public number n, okay, that's not impossible. Sorry, that is impossible because it takes too long time to count. Okay. Now Alice choose a number. Alice choose just option number. Chooses a number e. Co-prime with phi n. Co-prime is phi n. Let's see phi n. Because Alice has phi n, so he can easily find a number co-prime with phi n. i.e. E, GCD, great common divisor, E and phi n are, this is the one. Okay. And choose D. Such that D times E is the inverse. Modulo phi n. Okay, modulo phi n. Here, D is private key. D can be uniquely determined by this congruent relation. D is the private key. So D is private key. Only known, kept by Alice. Nobody else knows this D. Now E is E. So the public information is this. Public information. So public information is this. N. You write this number N as decimal numbers. Hundreds of digits of this N. Okay, and this number E. So this is public. Everyone can know this. Okay, so Alice can even publish this number, publish this N and this number E on New York Times. Okay, so this makes the communication easier because it's public key. So this is actually public key. So everyone can use this key. Okay, now private key. This private key is only known by Alice, phi n and D. This is private key, only known by Alice, known to Alice. Even Bob doesn't know this. Okay. So the private key is only known to Alice. Now this is better than the Hill cipher. Okay, the Hill cipher. The Hill cipher is not good because the private key is shared by Alice and Bob. Okay. Now suppose Okay. So Alice has public key. So suppose Bob wants to send a message M. Suppose Bob wants to send a message to Alice. To send a message. See the message M to Alice. Okay. What this does is the following. Okay. Now this Phi is really large number. So a reasonable message is, you write a message like code a message by a bunch of numbers using we have a lot using maybe ASCII code. We can transform a string of text into a number. Okay, into a number. So we can assume M is less than Phi. Okay, N is large. Phi N is also large. Okay, so M is a number less. So the message we can just encode a message just by a number. Okay. So this Bob, because Alice already published her public key N and E. Okay. So what Bob does is Bob. So suppose this is Alice. This is the Bob. So this is the public key is known to everyone. So the message M that Bob wants to send to Alice. So Bob do the thing encode. So message M, that is what Bob wants to say, encode to M to the power E. Okay. Now E is public. Okay. Now and then E is this mod N. E and N, they are public. And then send this message. Send this to Alice. Okay. Send this to Alice. So send this to Alice. Send it to Alice. Now Alice can recover this message. Okay. So then what Alice does is so let's see, suppose this number is received by Alice. Let's see R for receive. Okay. Alice now use her private key, compute R to the power D. Okay. D is private key. Okay. R to the power D, which is M to the power E to the power D. Okay. Now this is M E to the D. Remember E to the D. Remember E to the D is congruent to 1. E to the D is congruent to 1. Mod Phi N. Okay. So we can write E D. The product is 1 plus some multiple. Let's see multiple L of Phi N. Okay. So this will be congruent to M 1 plus L times Phi N. Now if you write down this, so this will be M times to the power 1 times M to the power L of Phi M to the power L mod N. Okay. Now M to the power 1 is just M. Now M to the power Phi, remember M is co-prime with N. Okay. So M to the power Phi N is the group order. Okay. So you get actually this should be 1. Okay. M is co-prime with Phi N. Sorry, M is co-prime with N. Okay. So this to the power Phi N, you get a 1. Okay. 1 to the power L mod N. So you see this 1 to the power L is again 1. So Alice finally recovered the message M. Okay. Recovered the message M mod N. So Alice recover or decoded the message. Decoded the message M, you see, to the power 1 M. So we recovered the number M. Okay. Okay. Now this private key is kept by Alice forever, and the public key. Now Alice, suppose Alice want to communicate with other people. Let's see, Peter. Alice want to communicate with Peter. Then Peter does the same thing. Send her message, use her message M, and then to the power E, and then modulo N, do the same thing. Okay. So you see here the advantage of this algorithm is the private key is only kept by Alice. So Alice can use her public key, okay, public key to communicate with other people, and then use private key to decode the message, okay. So even if everyone gets the public key, now anyone cannot decode. Anyone cannot decode, okay. Anyone cannot decode, except Bob sends the message to Alice, except that Bob tell other people the message, what this message is, okay. If Bob doesn't tell anyone the message, okay, then other people, once any people, some evil people that even some evil people get M to the E, the message is sent on the public channel, okay. So M to the power E is what Bob sent to Alice over the public channel, over some information channel. Now, even anyone get this M to the power E, then because there's no, he or she doesn't know the private key, Alice's private key, so there's no way to recover M. So difficult to recover M without private key. Difficult. Very difficult to recover M without private key. Okay, so this is the idea of RSA algorithm. Okay. Okay, let's do some remark before we give example. Remark. So the security of this RSA comes from the fact that it's difficult to factor the product of two large primes. Okay, so remark. Let me make this bigger. Let me make a remark. The security of RSA algorithm comes from the fact it's difficult, time consuming, that it's time consuming to factor, or computationally expensive, consuming to factor semi-primes, i.e. n equal to pq for large primes p and q. Okay, on a classical computer, okay, why do I write down classical computer? This is because of a classical computer, the information stored on classical computer is 0, 1 using electric signal or something, or magnetic signal. Now, on a quantum computer, we can actually beat RSA. However, okay, we have quantum algorithm that can beat RSA, that we can factor PQ, the product, okay? However, a quantum algorithm exists. Now, quantum physics is actually quantum mechanics. I mentioned earlier, quantum mechanics is actually, a physics rule, a physics principle describe. Our rule is actually quantum. But on large scale, the quantum effect is not very, we don't see very, because the quantum effect is not clear for large object. Okay, but the rule is actually the quantum theory. Okay, quantum theory. So we can use quantum rules to build a computer. Okay, build a computer. And then this quantum computer will be more powerful, a quantum algorithm. So this can be achieved on a quantum computer. However, we cannot achieve the quantum algorithm on classical computer. So this is called Shor's algorithm. I think this is just the Shor algorithm is I forget the exact time how Shor is published his algorithm. So it's just a few years after RSA. Shor algorithm is quantum algorithm that use this quantum algorithm we can actually factor easily. So this can beat RSA. Once we have a reasonable computer, now actually right now we already have a reasonable. So right now we already have quantum computer, but the number of there are still some technical things that prevent us to build too good a quantum computer. Because the quantum information is hard to preserve its quantum effect. Okay, we don't need just we not just need a quantum algorithm. We also need certain things that can achieve the algorithm. Okay, we need to preserve the quantum information. Just like you need certain things that preserve the classical 0-1 information on a computer. Okay, so there are some technical things that we still not achieved from engineering of a quantum computer, but the algorithm is pretty good now. So once we have a reasonable quantum computer, RSA will no longer be secure. We will no longer secure. Okay, so you see one of the reasons that you see quantum computer is so powerful. Okay, many things that we cannot do on classical computer can be done using quantum computer. This is, you see, currently many things is actually use RSA algorithm. Now, once you have a quantum computer, you can actually beat the RSA. You can you see many things will be not secure. Many information will no longer secure. So this is actually why quantum computer is so active research area. Okay, there are many projects supported by, for instance, DARPA. This is a supported this kind of a research on quantum computer. Okay, now let's do some example. Of RSA. We have 25 minutes, so we should have enough time to do one example of RSA. Okay, good. Let's do one example how RSA works. Okay, let's see baby example. Let's now do one baby example of RSA. Okay, baby example of RSA. Now, of course, we just So choose really not too large number because we don't want to that too complicated. So suppose we have Alice, we have Bob. Now suppose Bob want to send a message. Suppose the message equal yes. Okay, the message is yes. Now Bob want to send the message yes to Alice over certain public channel, the public channel. So now Bob want to make sure that this message is not stolen by, is not known to any other person. This now this is not possible. It's not possible that Bob send directly yes. Okay, because everyone get this message will just get this information. So let's assume that Bob want to send Alice a message. Let's use yes message. The message M is yes. Okay. Now Bob uses a standard ASCII code. ASCII code yes. EYYES. Now we have the ASCII code. Remember we just did it last time. Let's see the ASCII code. Let's see the ASCII code. Yeah. Let's look at the ASCII code. Look the code YES. Okay, YES. So Y, you see, Y is 121. 121. Look for Y and E. Okay. Now E is 101. Okay. S is 115. Okay. So we finally transform these three letters into a number. Okay. So Y is 121. Now E is 101. S is 115. So the number, so we get the number, the message. So the message is this number. Okay, the message is this number. Okay, suppose now now we do Alice. Alice choose 2 primes. Now suppose now I already choose the 2 prime for Alice. Okay, so the examples that I'm prepared. So P to be this number, Q to be this number. So this is not too large. This is not too large. Because so their product, we can find their product. So it's a reasonable size. Okay, reasonable size. Okay, so let's do it use a seed. Okay, so let's do P is 80273. Okay, Q is 49069. Okay, so phi n. Let's choose what notation do I use? Let A be phi n. So it's a P minus 1 times Q minus 1. Okay, so this A is private information. Okay, this A is private key. Okay, private key. So what is N? N is P times Q. P times Q. Okay. Okay, so this N is public. You see, the choice, my choice is not good because you see the A and N, they differ too much. Okay, so in theory you can just because the primes that I choose is not large enough. Okay, so if you choose large enough, there should be distinct. There should be distinct many digits. Okay, so let's choose E. For instance, let's E be 13. Okay, so the message M is, we already know, yes. Okay, 121 for Y, 101 for E, 115 is ASCII code for S. Okay, so this is the message M. Now let's see what Alice sent. Alice sent Bob. Alice sent the Bob public key. So, so let's see this. Okay, so Alice sent Bob. Now Alice can actually not send just to Bob. Alice can just public her public key on New York Times, for instance. Okay, so this public key 915 and 13. So this is N, this is E, this is E. Now, so this is public information, public information. So this is for instance available on New York Times. Okay. Now, Barber, what Barber does is Barber compute this. Barber compute m to the power 13, m to the power e. Okay, it's m to the power 13 mod n. Okay, so now m, I don't want to write out the message m, the large number again. So this maybe it's not too large. So it's 121 101 115 to the 13 mod n. I don't want to write n. It's okay, mod n. So let's use the calculator, use the seed to compute. Okay, let's use seed to compute. Okay. Excuse me. Okay. Okay, let's compute. Okay, m to the power 13. So we compute. So this is a message. Yes. Okay. Now n is the public key. E is 13. So we want mod find the remainder of this message m to the power. Let's see. Let's use e. Yeah. We want mod the remainder of the message m to the power e. Okay, to the power e mod n. Okay, so this gives you the remainder of this message. So this is the decoded encoded message. Okay, so this is encoded message by Bob. Okay, let me copy this. Okay, so Bob, this will be the Bob, what Bob encoded message by Bob. Let's make it larger. Okay, so this number is encoded message. Okay, the m to the power e mod n. Now Bob sends this number to Alice. Okay, Bob sends this number to Alice. So send it to Alice. Send to Alice. It's even possible that this message is sent over public channel. Okay, if anyone gets this message, it's still not a problem. Okay, so even Bob can. So this information can be sent over the public channel. Okay, send to Alice. So it's it's okay to send this information over public channel. Okay, now Alice. So R will be Alice receive this message. This will be 7. This number. Let me just copy it again. Okay, so Alice received this. Now received the message. Now Alice compute this. Now we need to compute e to the power d, r to the power d, which will be to recover. Okay, so we need to compute d. Okay, now we need to find what Alice private key is. D is Alice private key. D equal to Alice private key. Now we need to find what D is. Alice private key. Now we need to find the private key. Now how do we compute the private key? How does Alice compute the private key? Okay, remember we need to compute this congruence. E times D equal to 1 mod phi n. Now phi n is known only to Alice. So that because no one else knows phi n, so no one else can find D easily. Can find the private key by E. Okay, so now if you write down this, so you actually had 13 times D congruent to 1 mod what is this? Mod is n. This n is mod phi n. Let's see what phi n is. Okay, let's phi n is actually our A. Is A. Okay, phi n. This is our phi n. Okay, so this is actually mod this number. Make it bigger. Okay, mod this number. Now it's really inconvenient to write this. Actually, we can actually factor a factor. This will be you easily find this factor. Okay, now we solve this equation. So this equal to, so it's 13 13D congruent to 1 mod this number. Okay, mod this number. So you can, now we use some number theory technique. So you can actually solve this equation. 13 times D congruent to 1 mod 2 to the power 6. Okay, 13 times D. So you actually you get this D is 5. D is 5. You can check 5 times 13 is 65 mod 2 to the power 6 is 2 to the 64. Okay, so 5 is a solution. 13D is congruent to 1 mod 3 squared is 9. So D is actually tells us that D is 7 mod 9. 7 times 13 is 91. Okay, 91 is 1 mod 9. Okay. So also you get 13 times D congruent to 1 mod 29 squared. Okay, so you check this, you got a D. D is 647 mod 29. Okay, this small number can be easily computed. And also you have 13D congruent to 1 mod. Okay, where does this number come from? 2, 3, 29, 47, 173. This comes from the factorization of the phi n. Okay, phi n. Okay, 13 times D mod equal to 1 mod 47. To solve and compute it use seed. Okay, D is 29 mod 47. Okay. You see, let's just do one example. For instance, how do we get solve 13D congruent to 1 mod 47? So actually, we want the inverse of 13 in mod 47. So you can use seed to do this technique. Let F be GF 47. 47 is the final is the prime. So you just compute F 1 over 13. Okay, 1 over 13. This gives you the inverse of 13 modulo 47. So you just click, you see you get 29. Okay, so this tells you that D should be congruent to 29. D congruent to 29 mod 47. Okay, now how do you get this congruent? 13D congruent to 1 mod 29. So you do this technique. Okay, did you see? Oh, sorry. Okay, then you see D congruent to 29 mod 47. Okay, now how do we solve 13D congruent to 1 mod 29? Well, we can do this. You see it again. You see it again. Do this. Let's, for instance, let H be integer mod ring 29 squared. Okay. Now we find the inverse of 13 in H. Okay. So we let H 1 over 13. So this tells you the inverse of 13 in this system, number system. So you see, this is, you get 1 over 13 in H should be 647. So this tells you that 1 over 13 inverse in mod 29 squared is 647. Okay. So according to and also we have another thing is modulo 173. Modulo 173. You see here, modulo 173, 13D. We also need to solve this 13D congruent to 1 mod 173. Okay, so D here, you get, what we get is, let's see, what do we get? So let's be, so let's F be this 173. Okay, so this is F. Okay, so we so this is F. So we computed the inverse of 13 in this finite field. Okay, finite field is just a 13 number system. Okay, so F, we computed 13 inverse in this number system, finite field. So you see, we get 40. Okay, so we get 40. So we get D should congruent to 40 modulo. So we get a D congruent to 40 modulo 173. Now, on the other hand, so the condition you can write down. So to write down the conditions, so you have a bunch of congruent relations. Okay, congruent relations. Now solve these congruent relations is actually not difficult. There's a theorem called Chinese remainder theorem. So you can solve this kind of a bunch of congruence. Okay, congruence. So so this side we solve the congruence. So you see 57, 647, 29, 40 mod 64, 9, 29, 47, 173. Okay, so we solve using Chinese remainder theorem. Okay, so if you study number theory, this Chinese remainder theorem will be not that difficult. It's not hard. Okay, so we use actually a black box. Use a black box. So Chinese remainder theorem. So we use seed. So this is actually already available. This computer, this algebra package in seed. So we can actually solve using Chinese remainder theorem. So use CRT, Chinese remainder theorem. Okay, Chinese remainder theorem. Then what we do is this. Okay, so write down. You have 5, 7, 647. Okay, 29, 40. Okay, 40. See the computer package. Okay. Then we have other numbers. 64, 9, 29 squared, 47, 173. Okay, so you write the congruence numbers. You have a bunch. You see this thing. We have 5, 7, 647, 29. and we have 40. Okay, the other numbers we write in terms of another vector: 64, 9, 29, 47, 173. Okay, then you write in different so you write these numbers in two vectors and then apply Chinese remainder. Okay, Chinese remainder theorem, and then you see we get this number. Okay, so this number is the private key. This is the Alice private key. Okay, D is Alice private key. So for this example, Alice private key is this D. Okay, so we get a private key. D is the private key. D is the private key. Okay, D is this private key. Okay, D is this private key. D is this private key. Remember, then what we did? We have the private key. So this is private key. Private key. Alice private key. So this is a keep private by Alice. Okay. Now Alice received the message. Now what so Alice does is apply this D, apply the message, received message D to the power of to the private key and mod n, okay, mod n. So the R, we already have it. Okay, we already received the R. Okay, so R is this number. Okay, D is this number. D is this number. N is we already have N. N is this number, huge number. So let's see R. Oops, sorry. What is what I did? I think we have okay, this is R mod. So here let's see R to be mod F to the power E mod N. So this is actually what Bob sent to Alice. Okay, so this number that sent to Alice. So Alice has this number, received this number, and then Alice does compute R to the power D and remember mod it by N. Mod it by N. So compute the remainder of this number, mod N. Okay. So you see, did you see something? We get this number 121, 101, 115. This is the ASCII code for YES. Okay. Okay. Okay, sorry. So you see, R is the message that sent to Barbara sent to Alice. Then once we have this message, Alice has this message R, and then he raised to the power D, and then mod to the power N. Okay, then what he get is 121, 101, 115, which is the ASCII code for YES, which is yes. Okay, so you see Alice get this number. So let's just go back to this one note. So Alice computed. So Alice computed this number. Maybe Alice see it again. Okay. This number you see, this is 121, 101, 115. This, and then if they both assume that they use ASCII code, they check back ASCII code. This is the little y, this is E, this is yes. So Alice received the message from Bob. It's just yes. Okay. Okay, so this is one baby example of RSA algorithm. Okay, and then how we use RSA actually to make our information secure over the public channel. Okay, so you can try to communicate with someone, use this RSA algorithm and choose some big primes. Okay, big primes. Okay, okay, good. I think it's good time to be stop here. Okay. We'll continue next week.